Okay. First we will show that this system which has 0 initial condition and takes x n and produces y s n, this is linear and shift invariant. And then we will show this overall system is neither linear nor shift invariant because of the presence of this y t n. Okay, this is very interesting. So, consider this system. To explain clearly, I just take a very simple example and you can generalize it to the general differential equation after that. That is y s n plus one differential equation I am considering a y s n minus 1 is suppose x n and initial condition is 0. You need only one initial condition here y s minus 1 equal to 0. Okay. Suppose I give an input x 1 n and it gives me y s 1 n. So, it will be satisfying this way y s 1 0 will be this initial condition is 0. If you put 0 here y s 1 okay, minus 1, whether it is y s 1 is to whatever initial condition is not given, that is all 0. So, that means this part is always 0. So, you get x 0, x 1 0, then y s comma 1 index 1, that will be minus a y s comma 1 y 0, y s comma 1 0, which is minus a x 1 0 plus x 1 1. Then y s 1 2 will be minus a okay, y s comma 1 1 plus x 1 2 okay, dot 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 dot. Similarly, if you give x to n y s to n, so we will get the same manner another input. So, y s comma 2 0 will be x 2 0, y s comma 2 1 will be minus a x 2 0 plus x 2 1 dot 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 dot. All right. Now, question is instead of giving either x 1 or x 2, suppose I give a linear combination of them c 1 x 1 plus c 2 x 2. Will the output will be c 1 y s 1 n plus c 2 y s 2 n? Answer is yes. Okay. That time your if you call y s 0, that will be new input. You are giving input now c 1 x 1 n plus c 2 x 2 n and we are calling it x n. So, y s that time corresponding output y s 0 will be new input x 0 and x 0 is c 1 but this much was your y s 1 0, this much is your y s 2 0, that is c 1 so at least at index 0 it is linear, that is total output is c 1 times output for system 1 case 1 and c 2 times output for case 2, that is case 1 means input x 1 n, case 2 means input x 2 y 2 n, sorry input x 2 n, right. Very simple, that is I am repeating again what I am doing. Suppose I gave x 1 n as input, corresponding output I denoted as y s 1 n. and I work out from this equation the values. Y is 1 0 is x 1 0, because this guy is 0 and we will have value minus 1, index is if n is 0, this total is minus 1. So, past samples are past values are 0 because 0 initial conditions are assumed. So, simply y s 1 0 is x 1 0, y s 2 1 will be minus a y s 1 0 plus x 1 0, and that I replace back and dot 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 dot. Similarly, I gave another input x to n, same way I find out the output. Then my question is, if neither I give neither x 1 nor x 2, but I give a linear combination, then called x n. X n is this. What will be the new output? So, new output again I have to solve with 0 initial condition. So, I know solution, if I call it y s n, y s 0 will be nothing but x 0, because past y s minus 1 is 0 because of 0 initial condition. So, y s 0 will be x 0, which is c 1 x 1 0 and c 2 x 2 0, but x 1 0 was y s 1 0, x 2 0 is y s 2 0. So, it is a linear combination of the outputs for the two cases, the same way. So, linearity is satisfied at n equal to 0, and then you can see linearity will be satisfied at any other index. We can prove it by induction. That suppose y s n is equal to c 1 y s 1 n y s 2 n for n up to say m minus 1. Then I will show it is true, we will show that it is true at n equal to m also. This is how I prove by induction. You remember you proved binomial theorem in school, a plus b whole to the power n equal to some formula. How did you prove? You assume that this to be true for n up to some index p, then you prove that is true for n equal to p plus 1, and then you validated this assumption by taking any special case. We have already taken the special case here, that at n equal to 0, linearity is satisfied by direct investigation. Now, I am assuming the linearity to be valid for n up to some index m minus 1, then we should show it is true at m equal to m also. So, which means it is true for any, if it is true up to n equal to say 0, say m is 1, it is true for m equal to n up to 0, because which is already the case we have seen to be valid. So, that is a valid assumption, but then this will mean it is true at n equal to m, that is it is true at n equal to 1, because m is 1. Then if it is true for m equal to 1, it is true for m equal to 2, n equal to 2, and dot 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 dot. So, what is y s m? From this equation you can take it to the left hand side, minus a y s m minus 1 plus x m, but I have assumed that up to index m minus 1 system is linear. So, if it is y s m minus 1, this will be c 1 times y s 1 m minus 1 by the assumption plus c 2 times y s 2 m minus 2, and x m I know it is always c 1 x 1 m, because I am giving this linear combination input, and then you combine, you take this together, one part here multiplied by c 1, take the c 1 out, a, and from here also c 1 out. So, x 1 m, and another part c 2, from here c 2 out. So, minus a y s 2 and from here c 2 out x 2 m, all right. And what was this part? from this equation, if I put m here, okay, this is within bracket, sorry. From this equation, what is y s 1 m? Y s 1 m will be a y s 1 m minus a y s 1 m minus 1 plus x 1 m, because that time input is x 1. So, this is nothing but your you put y s 1 m here, that is equal to minus a y s 1 m minus 1 and then plus x 1 m, because I am giving input x 1. So, this is y s 1 m. The same way this is also y s 2. So, that means at index m also, I should put it in bracket, sorry, at index m also output is linear combination of the two outputs. So, it is linear at index n equal to m also. So, if it is linear up to index n equal to m minus 1, it is linear at index n equal to m also, and it goes on. Okay. And how to show that it is true for up to for n up to m minus 1, at least one case directly we should show, that we have seen here by direct substitution, that is, I have assumed 0 initial conditions. Okay. What is y s n, y s 0, that will be given x of 0, but what was x of 0? X of n was the combined input. So, C 1 x 1 0, C 2 x 2 0, but what was x 1 0? X 1 0 was y s 1 0, because y s 1 minus 1 is 0 initial condition, and x 1 0. Similarly, so that is y s 1 0 is x 1 0, this I call that y s 1 0. By the same way, x 2 0 is y s 2 0. So, C 1 y s 1 0 plus C 2 y s 2 0, which means it was linear at index 0. Therefore, by that proof it is linear at index 1, because if it is m minus 1, that means m is 1. So, it is true at m equal to 1 at 1, and then if it is m minus 1, that means m is 2. So, it is true at 2 and dot 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 dot. So, at y s 0, y s 1, y s 2 all satisfy linearity, all right. So, it is a linear system. It is also shift invariant, because on the time axis at n equal to 0 I am giving the input, and before that system had no stored value, all output, all initial conditions, all past samples, past output samples, all past input samples, they are all 0. Past input was 0, past output was 0. System had nothing, no value. All past output samples were 0, all past input samples were 0. Okay. And then I gave input, I got a solution y n. Therefore, instead of giving at n equal to 0, if I hold that 0 initial condition situation for further and give the input at n equal to r, the new output will be same as the previous output, because still n equal to r, the same 0 initial conditions for output and same 0 value for input were prevailing. So, whatever happens started happening from n equal to 0 onwards previously, same thing will start happening from n equal to r onwards, because I gave the same input. On a time scale, my new input is a delayed version of the previous input. So, my new output will be a delayed version of the previous output, the same delay, which means it is shift invariant. If I delay the input by some amount, or current output also will be delayed by the same amount, or like if it was like this, now the same thing will start happening here like this. Okay. Because before this n equal to 0 system was at rest, all initial conditions were 0, all past output were 0 and all input were 0. Instead of giving the input at n equal to 0, if I continue that 0 initial condition and 0 input condition till n equal to r and give the same input, system will work in the same way, because system property is time invariant, it is not changing with time. So, I will get the same output on the same time scale. If I plot, input is delayed by r, so output also is delayed by r. So, it is shift invariant. Problem is, if I consider the total output y n, then we will see some difference. Suppose, because y t n is obtained from the initial conditions. Suppose I do this exercise, instead of giving the input at n equal to 0, I here in this system I extend the zero initial condition that is zero initial condition up to n equal to r, that is till n equal to r, this system its past output samples will be 0, past input will be 0 and then I give the input. So, input I delay, I delay it by r. Okay. So, I give a new input g n which is say x n minus r, this we have seen this shift invariant, this will be n minus r. But y t n has nothing to do with input, right. So, y t n will not be delayed. So, new output will be, previously I had total output was y t n plus y s n. When I gave x n as input, that was my output. Now, I am giving x n minus r as input, which I call the new input g n. Corresponding output, if I call it y prime n, that will be what? This part will be output of this system, this subsystem. This subsystem is shift invariant. So, therefore, we have already seen it is shift invariant here in this example, because initial conditions were 0. I am extending the thing. If I delay the input, start giving the input instead of at n equal to 0 at n equal to r, till that point of time system no output will be generated. So, output initial condition will be still at 0, input also 0. So, whatever I observed by giving the input at n equal to 0, from n equal to 0 onwards, same thing I will observe from n equal to r onwards now, if I give the same input. So, that is why this was shift invariant, which means this x n if I delay by r, new y s n will be delayed by the same amount. But y t n, because of this will not undergo any change, because I am giving input, delayed the input, this y t n will not be delayed by that, because y t n is not controlled by the input, it is controlled by another subsystem and governed by its the initial conditions. So, this will remain y t n as it is. So, but this is not equal to delayed version of this. This is not equal to, which means y prime is not a delayed version of previous output y n with the same amount of delay r. But you see, if y t n was not present, then this is shift invariant. All right. That means, if initial conditions were 0, y t n obviously has to be 0, because if the past initial conditions were 0. So, y t 0 will be 0, y t 1 will be 0, y t 2 will be 0. So, no y t will be formed. So, if this is absent, y n is y s n, y prime n will be y s n minus r, which means y prime n will be y n minus r, y n minus r. This will be equal to y n minus r. So, then it will be shift invariant. But as long as there are initial conditions which are non-zero, the overall system will not be shift invariant. Similarly, linearity can be viewed that suppose I gave 1 x 1 n here, I found out 1 y s 1 n, and output is y n as y t n, you can call it output y 1 n as y t n plus y s 1 n. Next time I give x 2 n, corresponding output so overall output will be now same y t n okay, y 1 n was had y t n is common, that has nothing to do with the input side, input is hitting this system and y s n is formed. Y t n is built in solution, built in from the given initial conditions, a built in solution, it has got nothing to do with the input. That is why y t n plus y s 1 n same y t n plus y s 2 n. But if I now give a linear combination, as a matter of fact a very simple linear combination, just x 1 n plus x 2 n. If the overall system is linear, my new output will be y 1 plus y 2, but it will not be, because what is the new new output. If I give x 1 plus x 2 here, this system is linear. So, it will produce y s n as just summation of y s 1 plus y s 2, right, because this is linear. So, now y s n will be response due to x 1 n, that is y s 1 n, and response due to x 2 n, that is y s 2 n. They were added, x 1 and x 2 are added in the input side, so output also added. So, up to this no problem, linear. Y s n will be summation of previous two outputs, one due to x 1, one due to x 2. But in this case, the total y n, if I call it total output y n, will be still summation of y t n only and y s n. Now, this y n, you can easily see it is not equal to summation of y 1 n plus y 2 n. It is not equal to y 1 n, y 2 n, because if you add the two, you have got y s 1 plus y s 2, they are present. Y s 1 plus y s 2, y s 1 plus y s 2, which is y s n present. But y t 1, y t n, they are added. So, it is twice y t n, but here you have got only one y t n. So, it is twice y t n. If you add them, here you get only one y t n. That is the reason this equality is not satisfied. So, it is not linear. But once again, if y t n was 0, if it was not present, that is initial conditions were 0. So, built-in solution was 0. So, if this is 0, if this is 0, then there is no problem. This part is 0 means whether you have got y t n plus y t n, that is twice y t n, or only y t n. Y t n is 0. So, 2 into 0 or 0, they mean same. So, y n will be just y s n, and y s n means y s 1 plus y s 2, that is y n will be y 1 plus y 2. Okay, linearity will be satisfied. So, this detailed thing shows that such a constant coefficient difference model, it has got two solutions. One is called steady state solution, one is called transient solution. Transient solution because it comes from the initial conditions, built-in solution. It basically they try to decay down if it is a stable system, and y s n is the solution driven purely by the input, but assuming system 0 initial condition system. Then overall thing is neither linear nor shift invariant, but this subsystem with 0 initial condition is linear, is shift invariant. But overall system will be linear and shift invariant if initial conditions are 0. Okay. Then the built-in solution is 0. We will assume for our purpose that either initial conditions are given to be 0, and therefore, there is no built-in solution, no transient solution. We are only giving this subsystem. Okay. So, that is linear and shift invariant. Else, we will assume that let there be initial conditions and a solution, built-in solution y t n, but for our purpose, we will be bothered about only this subsystem. We will consider the property of this. Once y s n is obtained, to that we will add y t n separately. But as far as analysis is concerned, as far as understanding is concerned, we will consider only this subsystem. So, in either case, we will take this constant coefficient differential equation to have 0 initial condition like this, and we will give input, find the output. The system in this case will be guaranteed to be linear and shift invariant. Okay. Then one last thing, we had taken DTFT, studied. One thing we did not see, but it is a very trivial thing. Suppose x n is a sequence, it has got a discrete time Fourier transform x e to the power j omega, that is summation DTFT at any digital frequency omega from minus pi to pi, put that omega here, carry out the sum. Omega is continuous from minus pi to pi, omega is not discrete. This is DTFT. Question is, if I give a new sequence G n, which is a shifted version n minus say k, what will be DTFT of this G n? Very simple, you run the same summation, and then G n is nothing but x n minus k. Now, here if suppose I bring n minus k here, That means e to the power minus j omega minus k, so e to the power plus j omega k has come in. So, I have to cancel it. So, I have to bring e to the power minus j omega k, and this is dependent on k, summation is over n. So, this can go outside the summation as common. And what is this part? N minus k, if you call m, if n is minus infinity, m also goes to minus infinity. If n is plus infinity, n goes to plus infinity, m goes to plus infinity. So, summation x m e to the power minus j omega m, which is nothing but original DTFT. So, original DTFT multiplied by e to the power minus j omega k. So, that means if x n has DTFT capital X e to the power j omega, if I shift it by k x n minus k, its DTFT will be original DTFT multiplied by e to the power minus j omega k. K is the amount of shift. Now, you consider the difference equation. Suppose I take DTFT on the left hand side and right hand side. So, again they will be equal. This DTFT is y e to the power j omega, take common. So, 1. This DTFT is y e to the power j omega into e to the power minus j omega k, k is 1 here, j omega. This will be original times e to the power minus j omega, instead of k it is p. So, p, and same on this side. So, from all of them I take y e to the power j omega common. So, 1 plus a 1 and here capital X e to the power j omega. Then this is capital X e to the power j omega into the power minus j omega, because k is 1. So, so on and so forth. So, you take this common and b 0, then b 1 e to the power minus j omega plus dot 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 b q e to the power minus j omega q. And if I now take a ratio, output DTFT it will be now. So, this is general difference equation. I have not even assumed this is linear simply invariant, that is whether the initial conditions are 0 or not. Irrespective of all that, this is valid. This is, I am telling you, I took a general difference equation, it may have non-zero initial conditions. So, overall solution of this may not satisfy linearity shift invariance, even then this is true. Now, I assume 0 initial conditions, meaning difference equation is linear, is a linear and shift invariant system. But for linear and shift invariant system, we have also seen output y n is convolution between input x n and the unit sample response. That is, to this difference equation with 0 initial condition, that is making it linear and shift invariant. If you give x n equal to delta n, whatever output you get, that is h n, and if you convolve between these two, then again same x y n you get. And we have seen that if you take DTFT here, it is a product of the two DTFTs, which means h e to the power j omega into x e to the power j omega is y e to the power j omega, or y, if you take this ratio, if you take this ratio, like this, then this is the DTFT of the unit sample response, which we say transfer function. Transfer function in frequency domain, for the time being we call it transfer function only. So, if the system is linear and shift invariant, then there is a definition of transfer function, because output is a linear convolution between input and unit sample response, and in that case DTFT of this unit sample response is an output DTFT by input DTFT, which we call transfer function. But if it is linear and shift invariant and the system is given by difference equation, and I am assuming system to be linear and shift invariance, that is difference equation has 0 initial condition. In that case, this will be equated to this, because y e to the power j omega by x to the power j omega is for a difference equation is always this, whether you have got 0 initial condition or not. But if we have 0 initial condition, then it is linear and shift invariant. In that case, this ratio is the transfer function, because if it is linear and shift invariant, then output y n will also be written like this, x n convolved with h n, and DTFT of h n, which is called the transfer function, which is this ratio. So, in that case this ratio itself will be the transfer function. So, in this case what is this transfer function? You see, it is a ratio of two quantity, a numerator quantity and denominator quantity. It is a polynomial in terms of e to the power say minus j omega. So, e to the power minus j omega to the power 1, e to the power minus j omega to the power 2 dot 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 here also. Okay. So, numerator polynomial divided by denominator polynomial, polynomial in terms of e to the power minus j omega. Since it is a ratio of two polynomials, we call it rational systems. Okay. That is all for today. By the way, if I give you a problem, if I give you a small difference equation and with some initial condition, you should be able to find a solution. How? You will consider the total solution as a summation of two solutions. For one, you will assume consider the transient solution, where right hand side will be 0, and build up the solution from the initial condition. And in another case, take the initial condition to be 0, steady state solution, put the input on the right hand side, calculate the output from the input only and from 0 initial condition. Then if you add the two solutions, you get the total solution. Okay. That is all for today. Thank you.